we we were talking. I think this is the last slide we were on. And I think I got sidetracked because as we were talking about this stuff, I was noticing that there are 10. It says that the number of observations is 10 here, and when we looked at the actual data, there are, count them, 1, 2, 3, 4, 5, 6, 7, 8, 9. I was like, why in the hell is it saying I have 10 observations if there are 9 cases in this small data set? So I figured it out, and I put it in as a sort of note in the recording that just went up yesterday of the Meanstructure Part 1, that I went back and looked at the data that I actually ran this with, and apparently what I did, the sort of rookie mistake somehow, when I imported it in, it imported this line, the 45, 72, and 1, that are the means, and it recorded this as a participant. So I brought the means in as a participant. So, it's a sort of a goofy mistake that apparently I missed when I imported the data in. The good news about that is because it's exactly at the mean for both of them, it has zero impact on the slope or the well, what it does change is like the estimate, say, for the variance. The variance estimate's likely going to be a little bit smaller because it's got something exactly at the mean. It's going to add 0 to the variance, right? There's one extra degree of freedom that has 0 variance at it. It's adding 0 to the sum of squares. So the variance estimate's not going to be quite right. And things like standard errors may be a little off. But the means and the coefficients are correct. So I was like, I thought about sort of redoing it, but I'm like, we already recorded half of it. I don't want to go back and redo that. So I just made a note about it that if you actually look at the estimates for like the variances and the standard errors, they may be a little off, but the regression coefficients and stuff are on, the means are the same, correct? But that's why we're getting the difference between this 10 here and the 9 that we showed in the actual data. Any questions about this stuff? We've talked about a couple different ways of doing it. This sort of manual way where I asked for it individually. And here I actually put, I put a mean structure or whatever. I regressed x on 1 as well, which then gives me back the mean of x, the 72 here. And when you do that using the mean structure equals true, it doesn't do it for the predictors. So anything that's in this exogenous won't be regressed on the 1 because it's sort of not necessary. We can just calculate the mean. We can just ask for descriptives, get the mean and variance for x. We don't really need to include it in the model. But for y, because y is dependent, it's an endogenous variable, it's computing the intercept and not the mean of y. So that's why for the mean of y, it actually puts those on there. It does regress onto anything that's endogenous. Takes that variable, regresses it onto the constant. One of the things is it's sort of like, how do we interpret, an intercept? What does it actually mean? And this is something we've talked about before in terms of regression, right? How do you even interpret a intercept? And we got to think about, well, how was the data coded to begin with? And if you look at x back here, x doesn't have a 0. Right? So there's no meaningful 0 in this at all. So when it's computing the intercept, it's computing a value for what y would be when x is 0. So it's a sort of artificial, goofy number anyway, because it's sort of hard to interpret. And this is like, just to reinforce this idea, this is why a lot of SEM is basically done as a covariance structure, because we oftentimes ignore the intercepts anyway, because we're like, oh, it's not really meaningful, because 0 here is not even really a meaningful number on the x scale. All right? But there is something you can do when you think about this in terms of the models, in terms of interpreting intercepts. We'll get to in a second. So general principles about the estimation of intercepts and means and multiple regression. Let's just going over what I just said, but just make sure that everyone's on the same page. So when a criterion variable, right, an endogenous variable is regressed on a predictor and a constant at the same time, right? So we have both x and the constant predicting it. The unstandardized coefficient for the constant is the intercept. So that's how we actually get the intercept from it. However, when the predictor is regressed on the constant, that same coefficient is actually the mean, not the intercept. Right? So the same constant is going to give us both the means of predictors of exogenous variables and the intercepts of the DVs, of the endogenous variables with the same constant. Right? So when we look, that's what I wrote back here in this diagram, that because we're regressing our DV onto the ones, here we're getting the intercept, right? Because it's this and this are both predicting y, so we're getting the intercept. However, because there's nothing predicting x, this, by regressing x onto the constant, is going to give us back the mean of x. So path analytic principles about the estimation of intercepts and means. The mean of an endogenous variable is a function of 3 parameters. So wait, let's back up. So when we do this, we do a mean structure model, and we take our constant, and we take like y, and we regress it on the constant. It gives us an intercept. But what if I want, from that intercept, if I want to be able to estimate the mean of the endogenous variable, the DV, is there a way to do that? Can we actually do that? So if the mean of that endogenous variable is a product of 3 things: the intercept that we get directly from the constant, the unstandardized path coefficient from the predictor, from x, and then the mean of x. Basically what we're saying when we look at a picture like this one, right, is that y, right, y is dependent on x. So when we estimate the intercept here, there's some portion of this that is the intercept. The rest of the mean of y is actually dependent on x's mean. Right? So this slope says there's some proportion or some relationship between x and y. So there's some portion of y's mean is also dependent on x's mean. So we can actually use the slope, x's mean, to then figure out the rest of y together with the intercept and recapture the actual mean. So we can use these 3 things to then figure out what the mean is. That it's actually breaking the mean of y up into a part that's dependent on x and a part that isn't, and that's how we're sort of figuring those things out. Okay? So the model implied or predicted mean for an observed variable is the total effect of the constant on that variable. Model implied predicted mean for an observed variable is the total effect of the constant on that variable. All right, for exogenous variables, it's easy because there's just the direct effect is the total effect. There's no other effect, right? So we're going to take the unstandardized path coefficient for the direct effect of the constant is the mean, right? That's mean all by itself. For endogenous variables, the direct effect of the constant is an intercept, but the total effect is the mean. So think about this as a mediation problem. Go back to this picture. I should have included this picture again later on because it would have been easier to go back and forth. But if I look at y, I can think of x in relation to the constant here. I can think of x as a mediator, right? So there is the direct effect, which is the intercept, and then there's an indirect effect that goes through x. So if I take the mean that we get here times the slope, it gives me the indirect portion of y. And we add that to the direct portion, I can then recapture the mean of y. With me so far? So let's look at this model here, which is the one that we ran using the mean structure equals true. So I have x, I have y, there's a path between the 2 of them, I have my little constant, I'm predicting y with it, x with it. Actually, I'm not. So in this particular version, let's actually go back to the version before this. This is actually an easier version to think of. In this version, I actually have this in there. I have this part in the model. If we look at the path, the estimate here is 0.412. The estimate for the y-intercept is 15.362. The estimate for the mean of x is 72. All right, so the mean of y, the mean for y, is equal to that 15.362 plus, that's the direct effect. I need to multiply through. Remember the path tracing rules? I need to multiply through to get the same thing. So I'm taking that 72, which is the mean of x, times the 0.412. I don't know what's 72 times 0.412. Maybe with a calculator. 0.412. $29.664. Anybody else confirm that? So add 15.362 plus 29.664. What do you get? So the mean is 45.026, you said? Okay. So the model implied mean for y then is 45.026. What was the mean of y? It was 45. All right, so the model gets really close. This is sort of the model implied mean from computing the relationship between x and y and looking at the intercept and means here. We're actually able to pretty much recapture really close to what the mean of y actually is by combining the direct and indirect effect through from the constant to y and then also through x. Make sense? So this is the direct path, right? And then here this is sort of the indirect path. To make sure that I'm actually not drawing outside of the here. You can't really see that line, look, can you? Okay, so we got a direct and then indirect path, and we're sort of just adding them together to recapture the mean of y. That's not perfect because this is the sort of model implied mean. It's not the mean, it's the model implied mean. Just like we get a model implied covariance or a model implied variance, they should be close, especially with the model something this small, but they're not always going to be exact. When we talk about means and intercepts, it's not that the mean of y is not in the model, because we're talking about the intercept. It's just that the mean of y is getting split up into multiple parts the same way that the variances and covariances are. So we usually talk about the intercepts because it's the sort of direct effect from the constant to an outcome. The indirect effect captures the rest of it. It gets a little complicated too when you have multiple indirect effects or multiple direct effects through variables. It gets kind of complicated, but you just got to sort of multiply through and add everything together. The parameters of a structure equation model with a mean structure include more than what we've typically looked at, right? Before we had just just covariance structure. That was the only thing we really were looking at, which is fine. But we couldn't do means or intercepts. So there's more information. There's more data to analyze. Before we just looked at the variances and covariances of the model. Well, now we got the variances, covariances, and the means. So our typical way of looking at degrees of freedom and model fit and identification and stuff has to be tweaked a little bit. We can't just rely on just the variance covariance matrix. We have to also look at the means to figure out if we have enough data versus enough relative to free parameters to estimate in the model. And sometimes it can get kind of tricky. And often the way it gets described in most books, and I think part of what I'm going to show you now is not quite right. And I'm not sure why it gets described this way. But we're going to obviously look at the means of the exogenous variables are going to be parameters that are going to be added in. Intercepts of the endogenous variables are going to be added in. and the number of parameters in the covariance portion of the model are also counted in the usual way. So there's more things going on. We got to think about more issues, more ways in which you can have problems with identification. Okay. So this simple rule, this is from Klein. I've seen this other places, and it sort of is right, but not quite. It sort of bugs me a little bit. So a simple rule for counting the total number of observations available to estimate parameters of a model with a mean structure is P times P plus 3 divided by 2, where P is the number of observed variables. So before we were doing like P times P plus 1. Now it's doing P times P plus 3 divided by 2. The problem is this actually looks at the number of available like data points as sort of one thing, like sort of monolithic sort of thing, when really it's split into two parts. So this is always, I mean, this is there. You're going to see these other places. It always sort of, it's not quite right. It's not the whole picture. All right, so in order for mean structure to be identified, the number of its parameters, the exogenous variable means and endogenous variable intercepts, cannot exceed the total number of means of the observed variables. So think about that for a sec. Let's stop there. What does that mean? So I have the total number of means. So there's some number of means that are available, right? So if I have 10 variables, I only have 10 means. Make sense? So I can't estimate more means or intercepts than the total number of means I have in the data set. That's simple, right? 10 variables. At most I'm going to get is a combination of 10 means and intercepts. I can't do any more than that. So this means that we now are, so instead of this P times P plus 3 sort of overall sort of model fitting or identification issue, we really have to think about the number of means or means and intercepts we're estimating, and the number of variances and covariance we're estimating sort of separately. So we need to be able to be able to identify the model based on the variances and covariances, and at the same time based on the means we have available in the model. It's not like one thing. You can't like borrow from the other. Like if I don't have enough variances and covariances, I can just take from the means. It doesn't work that way. They sort of are separate. The identification status of a mean structure must be considered separately from that of the covariance structure. Right? It's a separate thing, separate issue. If that's true, why then in the same breath, as the book mentioned, this is acting like it's one thing? Well, it's not. It's two different things. You got to look at the means and the variances and covariances separately. So an over-identified covariance structure will not identify an under-identified mean structure and vice versa. What does that mean? An over-identified covariance structure will not identify an under-identified mean structure and vice versa. So let's talk about it. So what does it mean if I have an over-identified covariance structure? Now, what's the easy way to explain that? All right, so if my variance covariance portion, right, if I have positive degrees of freedom, right, because that's what it means, I have more data points than I have parameters, right? So I can, when I subtract, I actually have some degrees of freedom. That means it's over-identified, right? But if in my mean structure, if on the mean part, if I have negative degrees of freedom, which means I'm trying to estimate more means than I actually have available, this won't make up for this. Like I can't borrow degrees of freedom from the variance covariance matrix or the variance covariance portion to make up for the fact that the mean structure doesn't work. Or for in the same way, if this is positive, the mean structure part is positive, but the variance covariance part is negative, I can't borrow degrees of freedom there to make it work either. So it's almost, I have to look at identification of these two things sort of separately. The mean structure part needs to be identified, and the variance covariance part needs to be identified separately, and one cannot help the other in terms of identification. So read that again. An over-identified covariance structure will not identify an under-identified mean structure, right? So if I have positive degrees of freedom here, over-identified, it won't help the fact that this has negative degrees of freedom, and vice versa. Okay? And you might be having a tough time sort of picturing, well, why would I be trying to estimate more means than I have variables. That doesn't make any sense. Yeah, but wait. There are times when that will occur, and people oftentimes don't think about it until they're there, and all of a sudden they're getting these error messages saying that the model's not identified, and they can't figure out why. If the mean structure is just identified, it has as many free parameters as observed means. Okay, so that means I have 10 variables, I have 10 means, and in my model I'm estimating 10 means and intercepts. Great. I have a just identified mean structure. With me so far? Model implied means, like total effects of the constant, will exactly equal the corresponding observed means. All right, so then it's likely this thing when we were doing this a minute ago and computed, based on this one, when we computed the y means, likely we didn't get exactly 45, it's likely because of rounding. We're only rounding to 3 here, so maybe it wasn't just the model implied mean, it was just that the mean was, we weren't getting exact numbers because of the limitation in the rounding or something like that. This is saying as long as you actually include everything in there, you should be able to recapture the mean exactly. Fit of the model with just covariance structure will be identical to that of the model with both covariance structure and the mean structure. The reason why is when we look at model fit, it doesn't look at the means. It only looks at the variance covariance structure is what looks at the fit. The mean structure part does not get involved when looking at the fit of the model. Like the chi-squares and all that stuff are not included when looking at the model fit. So the model fit will be the same whether it's mean structure or covariance structure, but you won't be able to run the model if you try to under-identify the mean structure component. It's only when the mean structure is over-identified, meaning that you're trying to estimate less means in the model than you actually have means in your data, then you start to have differences between the real means and the model implied means. That is, one or more of the mean residuals may not equal 0. You may start to get differences between the model implied mean and the actual means from the data set. But for that, you have to then, estimate less means than you actually have in your data and have an over-identified mean structure component. The most general estimation method in SEM, this maximum likelihood, can also, be used to look at the mean structure parts. However, not all standardized fit indices for models with covariance structure only may be available for models with both of them. So certain ones may drop out. You may not be able to get the same ones. This is especially true for incremental fit indices, such as CFI, that measure the relative improvement in the fit of the researcher's model over a null model. It's likely for things like CFI, most of the fit indices, that the means will not even be included whatsoever. It's just going to look at only the covariance structure in terms of fit. That's usually sort of how it's done. The fit is looked at the covariance structure. The means are being estimated. The only time where the means will actually be brought in and what may affect the fit is when, if you're doing like a multi-group model and you're starting to constrain the groups, constrain across the groups their intercepts and means, then that'll start to affect the fit. Because now you're trying to force them to be equal, and it'll actually then it may actually cause misfit if the means aren't quite equal. When only covariances are analyzed, the null model for incremental fit indices are typically the independence model, which assumes 0 population covariances. However, the independence model for an incremental fit index is more difficult to define when you have covariances and means, because is it, what are we actually assuming there for independence model? It's independent, but for the means, are we assuming that the means are 0? Are we assuming the means are some population value? Like, what are we assuming is the null model for the means in an independence model when you're looking at assuming that the covariances are 0? So it's not really straightforward what that sort of worst model is when you include means. An alternative independence model allows for the means of the observed variables to be freely estimated, like they are not assumed to be 0. But again, it's not really clear, like, should we do this? Is there some fixed value for the means we should be looking at to compare our means to see if it fits? It's not really clear how exactly the means would fit into those relative fit indices where you have to use an independence model to establish that worst fitting model. All right. So here's where things sort of get interesting, and it's where the uses of mean structure become a lot more interesting than just in a path model. This is depression, predicting 5 items on depression, like a depression scale. And we're bringing in this constant to predict the factor. And here, in terms of so let's think about this. If I do this model, if I run this, what's going to be my degrees of freedom for the covariance structure? And how would I figure that out? So the covariance structure stuff we've already talked about before. Let's talk about that. How do we actually figure out degrees of freedom for the covariance structure portion? Forget about the constant for 1 second. Just look at this as a covariance structure confirmatory factor model. How would I figure out the degrees of freedom for this? Like, is it just identified, under-identified, over-identified? How would I look at that for this model? So I need to do 2 parts to that, right? I need the number of data points. And this is for the covariance structure part. Number of data points, and I need number of parameters. Right? Those are the 2 things we usually use. Subtract those to figure out what the degrees of freedom are. So how do I figure out the number of data points? What's our little equation that we've been using for a while? Yep. So we get P times P plus 1. All right, divide that by 2. So what's P here? Well, 5 items. So that's going to be 5 times 6, right, divided by 2. So 5 times 6 is 30, divided by 2 is 15 data points. How many parameters? And before you answer that, think about what needs to happen to make sure this model is identified. I'm not going to make a decision one way or the other. Seeing as how if I'm trying to estimate the mean of depression, I probably don't want to standardize this. Because I actually want to calculate the mean. If I standardize this, then the mean is going to be in standard units, likely something close to 0 or something. I need to, fix at least one of the paths to 1. Yeah, so I can fix this one. All right, and then we're going to estimate then this one, that one, that one, that one, and I also need to estimate the error variance there, and there, there, there. These are all 1, so that's nice. I don't need to estimate anything about those. That's nice. Simple. So looking at that, oh, and then one more for D1. I got one there too. Okay, so I need to, okay, well, here's the goofy part about this actually. If there's no constant, there's no D1. If I'm looking at just a covariance structure, I'm really just looking at, but there's going to be some variance associated with the factor on the other. So that's 1 for that, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I think there are 10 parameters, unless I'm counting wrong. All right, so that's 15 minus 10. There are 5 degrees of freedom. Right. Pretty straightforward. But what about the mean part? What is my number of data points for the mean structure? So for that, again, forget about that P times P plus 3 weird thing that was over there a second ago. If you think about, I have 5 items, that means there are 5 means. That's it, 5 means. how many means am I estimating? Well, for the mean structure part, there are 5 means. I'm estimating how many means? The only depression is being regressed on the constant. Just one. So for the mean structure part, right, there are 4 degrees of freedom. Right, so I'm over-identified here, over-identified there, which means I should be able to fit this model. I should be able to estimate the model because both the mean structure and the covariance structure are both at least just identified, but in this case they're both over-identified. All right. Well, that's what I was saying before. If either one of them are under, then the model can't be estimated. Right, so if both are under, then that's obviously a problem. But even even if we get degrees of freedom for the covariance structure part, right? So this is over-identified, but this is under-identified. The model can't run, and you can't shift degrees of freedom from here to there, right? Like that's what this slide a few slides ago, or whatever, was saying. This an over-identified covariance structure but not identified an under-identified mean structure. I have to have degrees of freedom in both parts, the mean structure and the covariance structure. All right, so you have to look at them sort of separately. So if you were like me and thinking about this, you may be thinking, well, why would I ever, under-identify the mean structure? It doesn't make sense. So I have 5 variables, I'm only going to want 5 means. Well, let's talk about that. And how sometimes that can be problematic. There's stuff we want to do sometimes that we can't. Then we have to make decisions about how to do it in a way that isn't what we want, but at least it'll actually be identified and run. Here's an example where you might have a problem. So what am I doing here? So here I am the CFA model with a mean structure that relaxes this for factors and indicators. So instead of assuming that the intercepts for all the items in the factor analysis are 0, we're actually estimating them. So we're going to estimate the mean for depression because it's an exogenous variable. So we're getting the mean here. But each one of these, this is going to be an intercept for item 1, an intercept for item 2, even though it says item 1, an intercept for item 3, intercept for item 4, intercept for item 5. Because that's where actually we're able to get what the intercept values are. So what is the actual level, like the level of people who are actually responding to this item? Now it's not the mean because it's dependent on depression. So we'd have to use the path to multiply that by the mean for depression, which is this here, to actually estimate the mean of item 1. But at least we're getting an idea of the level related to depression and what the intercept value is. You might be thinking, well, why do I care about the intercept value? Something we're going to talk about at the very next topic is looking at sort of item analysis and things like classical test theory. In factor analysis and everything we've done in here related to like to CFAs and factor models in general, we typically only care about the loadings, and loadings tell you how related the item is to the factor, how related the item is to the construct you're trying to measure. In classical test theory, instead of just test theory, psychometrics in general, that property is called the item's discrimination, how discriminating the item is, right? The higher the loading, the better discriminating the item is because it's more related to the factor. But in classical test theory and in test theory in general, there's another property we typically look at and we actually are interested often more, which is the item's difficulty. So if you're giving a test, whether it's standardized test or something like that, you not only want to know that the item relates to the thing you're measuring. So let's say it's a math test. I not only want to know that the item relates to the math construct I'm measuring or testing people on, but I also need to know the item's difficulty, because more difficult items, the students answer the more difficult items, they should get more credit or something than they're answering easier items or something like that. It should be more. There should be more information there. So by bringing in the intercepts of these items, we can now think about not only the loadings now or the items sort of discrimination, but we can also look at the levels of the items to see the items sort of difficulty, which we'll come back to very shortly. So we can now estimate both level, like difficulty, and discrimination simultaneously in a factor model, would typically be just focused on the loadings, the discrimination part of it. And that's going to segue us into IRT, because IRT builds in to how that works, both difficulty and discrimination, why it's used for things or by places like ETS to do like the SATs or GREs, these computer adaptive style tests. You can't do that with just discrimination. You need the difficulties as well. So planting that seed now, because we're going to come back and talk about that in just a little bit, like the very next topic. All right. So what's the problem here? Can I actually run this model? Yes or no? Why or why not? Would this model be identified? Yeah, but a standard CFA. Right. This is not a standard CFA. Standard CFA does not have, the standard CFA does not include a mean structure, and this constant's not in there. Right? This will not be involved. The problem with the way, and I know when you're looking at this, the problem with the way that this is written is this looks like it's just a measure predictor. This looks like it could be just like a mimic model or something. This is not. This is why I actually like the triangle more than the square. Because the square makes it seem like it's another measured variable. It isn't. It's not a variable at all. It's just a constant of ones. This is that the ones that we get in that sort of triangle that we did earlier. This is the same thing. So when I regress depression onto that, this pathway is going to tell me the mean for depression. Because I'm regressing item number 1 here onto that, this is going to tell me the intercept for item 1. It's the intercept because item 1 is dependent on the depression factor, right? So it's endogenous. So this is going to give me the intercept. Because depression has no other predictors, it's a exogenous variable. This is the mean for depression. Okay, that makes sense. All right, so let's go back to the thing we just did a second ago. Would the degrees of freedom for the model change for the covariance structure? So in the covariance structure, is this still identified? We still are going to have, I mean, the number of items hasn't changed, so it's still 15 data points, right? That hasn't changed at all. How many parameters? Nothing has changed. This is still going to have to be fixed to 1. So I'm going to have 1, 2, 3, 4 loadings, 5 errors. So we got 9, and then we're going to have at least 1 variance, whether it's disturbance or not for depression. So it's still going to be 10 parameters. So that's completely, nothing's changed on the covariance part. So we're still talking about 5 degrees of freedom. Great. What about for the means? So we have 5 means. That hasn't changed. Right? It's only 5 measured means, only 5 variables, right? How many means are we trying to estimate? Or how many means and intercepts are we trying to estimate? Not 10. So we have the 1 going to depression, and then we have 1 for each item. So all of a sudden we're trying to estimate 6 means / intercepts. Right? So I have -1 degrees of freedom. So a model like this is not identified. I don't have enough degrees of freedom in the mean structure part for this to be estimated. So if you try to run this, you're likely to get an error saying, you know, not enough or negative degrees of freedom or something, depending on the program you're using, because of this. And it won't even let you estimate the covariance structure because you don't have the mean structure set up. So even though we're going to only use the covariance structure components to look at the fit, like we're only really looking at this for fit, the model won't run if the mean structure part is under-identified. And even though I have 5 degrees of freedom just sitting here, they're untouchable. I can't use them for this. Like they're looked at separately. The mean structure has to be identified, and the covariance structure has to be identified separately. Okay. So how can I get a? Oh, go ahead. Question? No, go for it. Yeah. What's your question? So, you know what I was about to ask? How would you fix this model if you can't be able to ask that same question? So how would you? So what can we do? So we have this model. We want to be able to run it. We want to be able to use it. I want to be able to know what the item intercepts are, and I also want to know the mean of the factor. So what could I do? There's multiple options, not just one. But what's one way you might approach this and fix it? Be able to estimate those things you want with still being able to have at least 0 degrees of freedom. I mean, it at least has to be just identified, if not over-identified. How could you fix it? If this was you and your advisor told you that they wanted the mean of the factor, the mean of all the items in this thing in a mean structure model, how could you do that? So, I mean, if we add another item, I'm still going to want the mean for that item. I'm going to be back at having 6 means and 7 estimated. So no matter what. Yeah, because we want the factor mean, we're trying to estimate too many means. That's what I'm asking you. How would you do it? So you could, one option is to just not estimate the factor mean, right? Get the item means first. Don't estimate the factor mean. Because then I'd have 5 intercepts, 5 measured means. I'd have a just identified model, right? And then I could separately go back, run it again with just this here and not those. And I'd be estimating 1 mean with 5 measured means, so I'd have 4 degrees of freedom. I may have to do it in 2 different models just to make sure that that we're actually that we actually have enough in the mean structure part to estimate. So you can do that, but that requires you to run the model twice and to estimate the different things, which is not the end of the world, but it just means sort of tweaking things a little bit to get estimates for the mean structure part separately. How could I do this as one model without doing that? How can I actually bring in more degrees of freedom than I have? How can I actually, what kind of thing could I do to make it so I could have more means in here without changing the model? I mean the model structure. Still have 5 items, still have depression predicting the 5 items, so I'm not adding more items, but I do want to add more degrees of freedom. So how could I do that? And this is actually a special use case for this kind of thing we've talked about before as a way of bringing more degrees of freedom to be able to test a model like this and look at the mean structure for more than the number of means you actually have. So it's a bit tricky. It's like a little almost seems a little underhanded or something. It's like using a modeling approach for things that it wasn't meant for, but it actually works and it does it pretty well. It'd be the same. I mean, I'm not sure why you'd want to do that. Could you do that? I don't think that. I don't think you can do that. Could you? But even if you could, you would still have the same problem of having 5 means plus the depression mean having too many. So multiple times over the course of the semester, I said one of the coolest things or the best things about doing models through SEM or through these sort of structure equation modeling programs is the ability to do this thing, be able to do this approach, and it applies to anything: path analysis, covariance structure analysis. Confirmatory factor analysis, structure regression models, growth models. It's a thing you can do within those models to test really cool hypotheses that you couldn't do before. It's not something we ever really thought about before. And it's a way of testing things like mediation and stuff in a way, or moderation in a way that is just a lot more sophisticated than we have instead of just cross multiplying things. And it's that feature of all these things we can use here to save our asses and be able to run this model without having to run it in separate models. What is that thing that I've said multiple times is like the best thing about this? We talked about it within the context of growth models, within the context of path models, covariance structure models. I mean, it was the backbone of all the invariance testing stuff we did with CFA. Right, and in what is that sort of in general? What is that approach? What kind of model is that? What do you have to have in order to be able to do that? Fixing paths across what? I have to have groups. Gotta have multiple groups. So we do invariance testing within this multi-group model. We're actually able to build in groups and be able to look at estimating paths separately in groups, usually because we want to show there's moderation. We want to show that one group is different than another. We're trying to, I mean, it's possible that you're actually trying to show generalizability. You actually don't want them to be different. You want to show that the groups are the same, especially with a factor model. Like a CFA or something, you oftentimes are trying to show that this factor model works for everyone, right? That it's generalizability. But so we do all this invariance testing stuff within the context of a multi-group model, and it's the multi-group part of all this that actually makes for some of the coolest hypotheses, right? You can actually compare means and regression coefficients across groups to be able to do basically like a hypothesis where I think these groups are going to be equal on their means but different on their regression coefficients, have very unique and sort of complex relationships between variables that we can't do anywhere else. We can't do in other types of modeling approaches like ANOVA or MANOVA, that kind of things. So the multi-group part is actually what makes it really cool. Like we can do that stuff. So thinking of that, how would a multi-group model help us here? How would it make it so we can actually run this model? How can we use a multi-group model to make this work? So walk me through the multi-group modeling approach again. What is it you do? Lauren, you have multiple groups, and you do what with it? All right, so you have multiple groups, and then you can constrain parts of the model to be equal. So if you want to compare the groups and say, hey, are these groups different or equal on the regression coefficients or on the loadings? We fix those to be equal across the groups. If it still fits, that means the groups are roughly equal on those things, right? If it doesn't fit, then it tells us that the groups are likely unequal across those things. But here's the main thing. Whenever I fix something, when I constrain it to be equal, what that does is it takes two coefficients. It takes like a B for group 1 and a B for group 2. Let's say this is group B1 for group 1, B11, B1 for group 2. If I force those to be equal, what it does is it takes two parameters that we're having to estimate, and it turns them into one parameter. Make sense? So it takes two estimates and turns it into one estimate. Whenever it does that, we get a degree of freedom. Right? We get 1 degree of freedom back, because here I'm estimating two things. Those two things now are being estimated by one thing. So I'm estimating one fewer parameter, which means I get a degree of freedom back. Your approach to a model like this one would be a little different, because here the goal of this, oops, wrong button. The goal that we actually want here is to estimate the means. I'm not trying to compare groups. I don't really want group differences. I'm not interested in moderation. That's not what I'm trying to do here. I just want some degrees of freedom so that I can actually estimate all these means and this mean at the same time. So if I pick just two groups I think are going to be equal, even if I just randomly split the data up into two groups, right? Create two groups, estimate this model separately in both groups, at least the covariance structure part of it, right? Make sure it all fits. Add in the mean structure and everything, constrain everything to be equal. So now all five, so we now have 1, 2, 3, 4 items, or 5 items for group 1, and 5 items for group 2. So it means I now have 10 means to play around with. Follow me? That should be the same means, but it's been doubled up. So I now have doubled up the number of means I have. And then when I go, instead of actually having to estimate 12 means, I'm actually only estimating 6 still, because I'm forcing them to be equal across the two groups. So instead of having 12 separate means and intercepts, I still have 6, because I'm forcing them to be equal. So now I have 10 means with only 6 estimates. So I now have 4 degrees of freedom to estimate the exact same thing. So it's a way around the limitation in degrees of freedom when it comes to trying to estimate both latent variable means and item means simultaneously. Again, you typically don't care about the actual group differences. You're not trying to show moderation. You're just trying to use the two groups to generate more degrees of freedom so that you can actually test everything you want all at the same time, the same model. Like I said, it's like using multi-group models for a reason that it's not really designed for, but it works. And people oftentimes will do that to be able to estimate everything they want all in one model. Well, at the same time, I guess, sort of testing for group differences if the group is really something meaningful, but oftentimes they're not trying to do that. They're just trying to trick the model into having enough degrees of freedom so they can actually estimate everything. Yeah, it's like, all right, I don't have enough degrees of freedom. So instead of just giving up, we're like, okay, well, how can we make some degrees of freedom? How can we actually make it so we have enough degrees of freedom to run this? So in the context of multi-group model, knowing that as you constrain things, it actually forces them to be equal, and it frees up degrees of freedom. So if you free up enough degrees of freedom that way, you now have degrees of freedom to test the whole model, estimate all the means that you want all at the same time. So it's a pretty smart use of a thing that's not really designed for that, but it's sort of a byproduct of it that you can actually use and make it work. That's pretty smart. So based on the principles that was talked about here, right? The direct effects of the constant in the model just presented on the endogenous indicator should be intercepts for the regression. Right? We're talking about this model still. The endogenous indicators should be intercepts, right? Because they have the factor predicting them. And the exogenous factor should be the mean. So we said this already, right? This is the mean because there's nothing else predicting this. But because these are now endogenous to the factor, those going, from the constant to the items are all the intercepts. This is just saying that, okay? However, the CFA model with the structured means just presented is not identified. This is just putting text to exactly what we just talked about. But it's because there are 5 observed means, but 6 parameters of the mean structure, right? So this is what we just talked about. One strategy is to assume that the mean of the factor is 0 and estimate all the intercepts and indicators. So we could leave this out or fix it to 0. right? And then estimate these. And then estimate only the intercepts and indicators. Or the flip side is, you could, if you just want to estimate just the factor and not the intercepts, you can do that too. If you don't really care about the item intercepts, you just want to know what the mean of the factor is. Like for instance, in a growth curve model, it's likely we just use the constant to predict the latent intercept and latent slope, and not all the individual items. Okay, we just want to know what the means of those two factors are. We can do that without having to do a whole lot of extra work. Okay. In general, factor means can be estimated in a CFA model. Okay, we said that right. The other way we can get around this is if it's analyzed across multiple samples. Right, so your answer literally is in the slides, but I was hoping you wouldn't look and have to think about it yourself. So is analyzed across multiple samples, and constraints are imposed on certain parameters of the estimates. Like you're looking for strong factor invariance. You want the loadings and the intercepts to all be forced to be equal. That frees up degrees of freedom. You can now test for all that stuff all at one time in one model. The most common strategy, so this is another way that this is done. It's not how Levon does it, but some other programs do this, is that you actually fix one of the factor means to 0 in one group, and then estimate it freely in the other group to see the significant difference, right? But we oftentimes just force them both to be equal and do it more like an ANOVA approach as opposed to a t-test approach. The factor means in the other sample are freely estimated, and their values are then, it's the relative differences on the factor means that are compared. Additional constraints may also be included cross-group equality constraints on the factor loadings and intercepts, which together test for invariance in measurement and regression. And if you can get strong invariance, you can then estimate all the intercepts and the factor mean all in one model because you're free to a bunch of degrees of freedom across the two models, and you have more data because you have 5 means in group 1, 5 means in group 2, so you now have more data to play with. You're able to reduce the amount of degrees of freedom you need, or the parameters you need, because you're now estimating one parameter for both groups, and you now have enough degrees of freedom to test the whole thing, and the model would actually work, assuming that the groups are actually equal. If the groups aren't equal, then you have a problem, right? Because now they're estimating different means, and constraining them doesn't fit, and they got other issues. So here you actually want groups that are equal. And again, you could just randomly split your data in 2, use those as 2 groups because you want them to be similar as possible, and then use that to generate those degrees of freedom and test the whole model.